So today we are taking that right triangle trigonometry stuff that we were reviewing and practicing yesterday, and we're going to be adding it into circles, which actually by the time all is said and done, you'll hopefully find is actually even a little bit simpler when we take a look at it. But we got to do a little work before then to be able to see that. So let's go ahead and find x in this particular diagram. Now notice that we built the triangle within a circle here. This circle happens to have a radius of 1. And we're building this, notice, based on this angle O, that central angle. Well, in the end, though, in this problem, all we really care about is the triangle. The fact that the circle was built around it didn't change anything. And so I'm interested in finding x. Well, and I have the one side that's 1. And remember our process for how we do these, we ask what do we call each of those sides, so like the x side. Remember that we're going from angle O here, because that's the one that we know is 72 degrees. And so side x is the adjacent. The side that is 1 unit long, that is our hypotenuse. So which of the trig ratios involves the adjacent and the hypotenuse? Cosine. It is cosine. And so I'm going to set it up as cosine of the angle, so cosine of 72 degrees, equals, and cosine equals adjacent over hypotenuse. So I put the adjacent on the top and the hypotenuse on the bottom. It doesn't matter which one we know or don't know. It only matters which one's adjacent and which one's hypotenuse there. All right, from here, I now need to solve this. And this is where this particular setup that we're going to be using a lot today makes life a little bit easier. Because what does x over 1 equal? Well, what does 5 over 1 equal? 5 over 1 is 5. What's 12 over 1? 12. What's x over 1? And so that right side, we actually can get rid of the fraction because x over 1 just equals x, which means that in order to find x in this particular setup, we don't need to multiply both sides by anything. We don't need to divide both sides by anything. All we need to do is cosine of 72 degrees. And that is all. When you do that calculation, you should be getting an answer of x is about 0.31. Check that in your calculator and make sure you are in fact in degree mode. Alright, so having found our x value, I just want to bring you back. Remember where we started from. This triangle that we are just working with and we just found x for actually exists within a circle. And as we're going to be seeing, this is a very particular type of circle because it is centered here at O, which normally stands for the origin, and that's how I intended it here. And then it also has a radius of 1. So the radius of my circle is 1. We actually end up calling this the unit circle, as we'll be seeing. Okay, we just found x. Please now find y. And you will hopefully find that it is also easy to do. So please find y. All right, so to find y here. So you still start by saying, what do we call each of the sides that are involved? And in this case, we're dealing with side y. What do we call that side if I'm still starting at this angle? Yep, that is the opposite side. And then I still have this side, the one that is 1 unit long. What do we call that side? Hypotenuse, yep, because that doesn't change. And so I know then that this one involves opposite and hypotenuse. So I go back to my notes if I've forgotten, and I look through my notes at the definition of sine, cosine, and tangent to see which one involves opposite and hypotenuse, and it tells me sine. Because sine equals opposite over hypotenuse. And so when I write this side, the right side of this equation, since sine equals opposite over hypotenuse, I put the opposite on the top, so that's got to be our y, and my hypotenuse on the bottom, so over 1. And now that we've set it up, now we just need to find our answer. And just like the last one, finding our answer is easy, because y over 1, that's just y. And so if I want to know what y equals, all I have to do is punch sine of 72 degrees into my calculator, and it tells me that y is about 0.95. Right, now having seen that, both of these problems worked with this same exact circle. It started with a circle that was centered at the origin here and had a radius of 1. Remember I mentioned earlier, this is called the unit circle. And all the work we're going to be doing here is going to be involved with the unit circle, because the unit circle, since it has that radius of 1, it has some unique properties, but then once we know those properties, we can extend that information to be able to deal with any circle. Now, before I give you the notes on this, there's something I want to point out. The x and y that we just found, I specifically chose to call them x and y. Did you notice why? Yeah. All right. But notice, the amount that I go over, isn't that x? Like the x coordinate? The amount that I go up, that's y, like the y coordinate. So actually, when I found x and y, it actually told me the coordinates of this point. So by figuring out that x and y value in the unit circle, I then figured out what are the coordinates of the point that goes with that angle on the unit circle. So that's where we're going to be heading. But we got to get a little bit of detail into our notes. I mentioned the definition of unit circle. I want you to have that definition in your notes as well. And then, as we take a look at the work we do with this, one other little detail is that we're going to be talking about a lot of angles. The angles and how we measure it are standardized. We're always going to be going from the same place. Whenever we measure an angle, we measure that angle from the right horizontal. So in other words, this is considered to be a 0-degree angle if we just go straight to the right. And then we go counterclockwise from there. And so you'll notice that by doing that, we can end up with angles that are anywhere between 0 and 360 degrees. And actually, as we'll see later, even beyond that. Now, in the unit circle, we've already actually figured out some other information that we use in that first one that we can extend to a generalization here. So like, what did I use? Sine, cosine, or tangent to find the x coordinate, how far I went over in our earlier problem? We use cosine. The same is going to be true actually no matter how we draw it and no matter what the angle is. We can figure out how far we go over based on cosine. And what did we use to figure out how far we went up? We used sine. And that too is going to be true in any unit circle, no matter what that angle is, even these angles that are getting bigger than 90 degrees. And by finding that, by knowing that cosine gives us the over and sine gives us the up, that means we can then know the coordinates, the x, y coordinates of any point on the unit circle by using cosine and sine. And so go ahead and then add this also into your notes for unit circle. And so this is really the big idea from today, is that if I want to know the coordinates of any point on the unit circle, I could do cosine of the angle to find the x coordinate, and I can do sine of the angle to find my y coordinate. And that is true no matter what. So remember, it goes cosine comma sine. That is x comma y. And if you remember that, you're going to be in good shape. You're going to be able to do problems like this next one that we're going to do together. So here we have a unit circle. The measure of the angle here is 108 degrees. And remember how we're getting that. That means this is 108 degrees in here. We're being asked to find x and y. Now before we actually do it, let's remember why we can know this and what we're doing in order to be able to get this. If I'm looking for the coordinates of that point, now I could go through the trouble of drawing in this triangle and dropping down the triangle, and then I could use that to figure out, okay, what's the angle in here in order to then find x and y. But I already know what I'm going to have to use based on the work we did earlier. I already know that my x I'm going to have to use cosine, and my y I'm going to have to use sine. This is just straight out of my notes. To find x I do cosine, To find y, I do sine, and so I can just go straight to it without even having to make that drawing. In order to find x, I'm just going to do cosine of the angle. That's all I have to do is cosine of 108 degrees. And then we can do that calculation. And in this case, it gives us an answer of about negative 0.31. Okay, and then we need to find our y value as well. In order to find y, we use sine. So I'm going to do sine of 108 degrees. And again, then all I got to do is just punch that in the calculator. And in this case, it tells me that y is about 0.95. These numbers seem slightly familiar. Do they seem familiar to you?
Yeah.
Because these are the ones that we came up with earlier when we were dealing with our other angle, our 72-degree angle that we started class with, except that there's one difference. Notice that the one difference here is that my x value this time became negative. But otherwise, the numbers were the same. Now, in terms of the actual angles involved, I'll let you ponder why they would be the same in this particular case. It's very particularly chosen, so that would happen. And we're going to be digging into that idea a little bit deeper here in the coming days. But do notice that we can get a negative number. Does it make sense that you get a negative number there? Well, and if you're not sure, think about what we're really looking at here with this picture. Those numbers are coordinates of that point. Remember, in the unit circle, it is centered at the origin. If I'm trying to get to that point, notice I'm going to the left in order to get to that point. That means that my x-coordinate then must be negative. And in order to get my y value, I'm going up. Hence why the y-coordinate is positive. And so you can see then, as we start moving this point around the circle, that you can expect that both of those coordinates will go through times when they're positive and times when they're negative. It's all going to be totally possible. All right, now I did say this is the biggest idea from today, but it's not the only idea we're touching on, because I also want to bring back some stuff that you also saw last year in geometry. I'm going to start with hopefully what's a simple question, although it can mess with our heads at times. What is the exact value of pi? Well, if we use pi like in our calculator, or we see it, we can see 3.14159 and so on and so on and so forth. But is that the exact value? No. Does pi ever end? No. And so when we talk about the exact value, this is one of those terms that we end up using a lot in this class and later on as well. When we talk exact value, there will be no numbers involved here. Because no matter how many digits I write with this, I can never actually write out the exact value. Because the exact value, it's irrational. It keeps going on forever. And so, technically speaking, if I want to write out the exact value of pi, I just write pi. So if I'm wanting to represent this exactly, I represent it using the symbol. The same thing is going to happen as we get into some triangles here. And so back in geometry, remember the 45, 45, 90 triangle? Notice in this case, I have already filled in one of the side lengths. I've already filled in that the hypotenuse is going to be 1. Well, that's because this is the common one that we're going to be working with. Again, because of the unit circle having a radius of 1, we're going to have a lot of hypotenuse of 1 as we go forward. All right, so then, do you remember what these values are? What the leg lengths are? Well, if not, I'm going to give you a very quick reminder about how we get them. I'm not expecting you to have to do it this way every time, but I just want to remind you why we can know it. If it's 45, 45, 90, that means it's isosceles, so I know these two side lengths are the same. And if those two side lengths are the same, let's say I call them x, then I could use Pythagorean Theorem, x squared plus x squared equals 1 squared, because it's got to equal the hypotenuse squared. And I could solve this. So x squared plus x squared is 2x squared, and 1 squared is 1. I could divide both sides by 2, so x squared equals 1/2. And then I could take the square root of both sides, so x equals the square root of 1, well, the square root of 1 is just 1, over the square root of 2, which is just square root of 2. Remember at the start of our last lesson, we rationalized denominators? I'm going to do the same thing here. I don't want to leave the radical in the bottom. And so I multiply the top and bottom of the fraction by the square root of 2, which gives me then the answer that you are going to get to know really well over the next few weeks. Root 2 over 2. And so then we can know that in a 45, 45, 90 triangle like this, that the two leg lengths are root 2 over 2 if the hypotenuse is 1. Now based on that, we can then actually know exact values for the sine of 45 degrees and the cosine of 45 degrees. Because really, if I think about the unit circle, go back to that idea that we've been working with so far today, I can see that we're actually working with part of the circle here. And really we're just working with just this part though. And so I could actually kind of build the circle around it if I wanted to, but this point up here, well, that's the point on the unit circle. And remember, I find the x value by doing cosine. And I know what that value is here. So the cosine of 45 degrees is the square root of 2 over 2. And the y value, that was our sine. And you can see here our sine, then our y value is root 2 over 2 as well. And so we can know those exact values. Please add those also into your notes. That the sine of 45 degrees equals root 2 over 2. And that the cosine of 45 degrees also equals root 2 over 2. All right, and now that we've seen the 45, 45, 90 triangle, do you remember the other special right triangle from last year? Hopefully you're thinking of the 30, 60, 90. And with the 30, 60, 90, we can also know the exact value of the legs if I set the hypotenuse equal to 1. Now in order to do that, again, I'm just going to remind you how that work gets done and what it looks like. You're not going to have to do this or replicate it often, but you do need to still have an idea about where this stuff comes from, because we don't want to just think, oh yes, it's math, therefore they're just magic numbers that somebody made up. We need to remember that these actually come from someplace. In the 30, 60, 90, we can actually find that by thinking about the other half of the triangle, because you'll notice that if I put that other half of the triangle there, that makes the entire triangle here an equilateral triangle. Well, that actually makes some of our life a little bit easier, because that means this length here, well, the whole length has to be the same as the other length that we already had, so that has to be 1, which means that this length has to be just a half. And so I can know then that this is a half. Now, if I know that is a half, then I can find the height. I might call it x there. Because you'll notice I now have a right triangle and I know 2 of the sides, so I could use Pythagorean Theorem again. I could do like 1/2 squared plus x squared equals 1 squared. And we could actually solve this through. I'll do it very quickly. So 1/2 squared is 1/4 plus x squared equals 1. Subtract the 1/4 from both sides, so x squared equals 3/4. We do the square root of both sides. X equals the square root of 3 over the square root of 4, which is 2. And so that's how we can then find that the other side, if my hypotenuse is 1, the other side then must be root 3 over 2. Basically, we found this. So we now know these values. And if we know these values, then we can also use them to find out what is sine of 60 and cosine of 60. Now notice I'm using 60 here because 60 is that inner angle. That is the angle where the origin of my unit circle would normally be. Now, if I want to find sine, remember sine is like my y value. Okay, what would my y value be? It's how far we go up, right? So it's got to be the root 3 over 2. And cosine, that's like my x value. And so if that's like my x value, that's how far I go over. And so then the cosine of 60 then must be 1/2, because that's how far we go over. Make sure to have these in your notes. Now, since we could know that for the 60 degrees, notice I could also use that to figure out the sine and cosine values of 30 degrees. Because again, I could think about it the same way. And notice I'm kind of getting you used to seeing these triangles built in there in order to connect them to the x and y. Sine, well, remember sine is our y coordinates, how far we're going up and down. So if I want to know what sine of 30 degrees is, I look at my 30, 60, 90, and I see how far is it going up. And notice sine of 30, because I put the 30 at the origin this time. And so sine of 30 equals 1/2. And cosine of 30, well, cosine is x. That's how far we're going over. And so that has to be the root 3 over 2. And again, have those in your notes.